So our next presenter is Dr. David Blewett, and he is presenting a talk on lunar swirls in the Mariah and Highlands, near ultraviolet and near infrared space weathering trends. So David, feel free to take over whenever you're ready.
Okay, how's my audio?
I hear you.
Okay, and you can all see the screen?
Mm-hmm.
All right, well, that was a great lead in from Nandita. I'm going to continue to talk about space weathering, except here in the near UV and the near IR, again, talking about swirls. So space weathering, well, as we know, rocks on the surface of airless bodies undergo a variety of changes as they're converted to soil. The optical changes are particularly profound. If you can see my cursor there, is illustrated here on the plot on the right, which shows lab reflectance spectra for a freshly crushed Apollo 15 Mare basalt and a mature soil of the same composition. And these optical changes are caused by accumulation of nanometer-sized metallic iron in the form of blebs and coatings on and within the soil particles. And this nano-sized iron is thought to be created during solar wind exposure and micrometeoroid bombardment, although the relative importance of these two agents is debated, and the relative fluxes of these change from place to place in the solar system, as well as place to place on the moon. So it's important to have a good handle on their effects. Now, magnetic anomalies. There are these magnetic regions of the lunar crust, and they provide really unique environments for investigation of a wide variety of questions in lunar and planetary science. The presence of a magnetic field attenuates the flux of solar wind ions that can get down to the ground to some degree. But the micrometeoroids are unaffected. So what you have at a magnetic anomaly is a natural space weathering experiment with a control on one of the variables. And as it happens, and as we heard in the previous talk, many magnetic anomalies correspond to these peculiar albedo markings called lunar swirls. Probably the most famous of which is Reiner Gamma, and maybe you all voted for that in Deborah's poll at the beginning of the session. So the goal of my work is to help gain an improved understanding of this optical space weathering on the moon and its causes through a combined analysis of swirls in these two wavelength regimes. But before we go to the moon and look at the remote data, it's helpful to have a framework for interpreting what we'll see, and that can come from laboratory spectra for Apollo rocks and soils. So I'll be talking about two spectral parameters, the near-infrared reflectance ratio at wavelengths of about 1550 and 750 nanometers. This is a measure of the near IR continuum slope, as you can see here in the middle plot, where the continuum slope increases for more mature materials. And then this near UV ratio of 321 over 415 shown here, that is a steeper slope in fresher materials, and this is related to the strength of an oxygen metal charge transfer absorption that extends into the ultraviolet. So we can plot up these parameters, these ratios, and look at how they vary with reflectance for the different lunar samples and with the I sub s over FEO maturity parameter, which is the ferromagnetic resonance parameter index that is related to the abundance of single domain iron. And I've divided up the lunar samples into these 4 categories: low and high titanium Mari samples, and then 2 in the Highlands, depending on the iron abundance. Now, another really valuable resource for helping to understand space weathering are these silica gels that were created by Sarah Noble and her collaborators. What these are transparent media that which are impregnated with nano-sized iron particles of different sizes and different abundances. So this lets us look at the spectral effects of those 2 factors. And so what I've done here, the 2 plots on the right, are I took the data that was this reflectance spectra for all these samples that were published by Sarah Noble, and converted them into these ratio reflectance plots for in the near UV part of the spectrum and the near IR parameter that I'm looking at. And this allows us to see the differences for the different size and the different abundances of these particles. All right, now onto the spacecraft data. Somewhat similar to what you saw in the previous talk, we have image data for a number of lunar swirls for the near UV. We have the LROC WAC data, and I'm using the Kaguya multiband imager for the near IR. And so at each location, we define regions of interest, different parts of the swirl, the dark lane, background material. And this has been done for 3 swirls in the Maria and 3 in the Highlands. So by extracting those pixel values from the images, we can create ratio reflectance scatter plots for the 2 different parameters. And what these allow us to see are just how are these materials, different surfaces, related to each other in these spectral spaces, from the bright swirl, edges of the swirl, dark lanes, background, and can do things like doing fits within each point cloud for a particular surface type. This lets us understand what's kind of going on within each type of material. I'm not going to talk more about that today, but that's something that's of interest. And in the interest of time, I'm just going to skip to some of the observations. One is that we don't see evidence for overmaturation in the dark lanes at the swirl, at least for the swirls we've examined. The idea here is that in the process of shielding the surface from the solar wind, the magnetic field may actually be channeling or focusing the solar wind into higher concentrated or higher fluxes in certain areas, perhaps those dark lanes that wind through the sinuous parts of so many swirls. If that were the case, you might expect that material will becoming kind of super mature, even darker and redder than the normal background, in which case you might think it would plot up here at a very low reflectance and a high reddish ratio. But we don't see that. The dark lanes generally seem to be transitional between less mature materials and the background. Of course, overmaturation could be taking place on local scales, depending on what we expect to be the very complicated and the very complicated nature of the magnetic field actually down on the surface. All right, so looking again at the comparisons with the Apollo samples, it appears that the swirl materials contain abundances of nano-sized iron that correspond to what the sample workers call immature or submature soils. So it's clear that the bright swirls are different from normal fresh material. And we see that here in this plot, which is this UV ratio and the reflectance, where each Apollo sample has been labeled with its ISOBS over FEO value. And then we see 2 of our other popularity swirl contestants, the Highland swirl at Gerasimovich and its nearby background. And then here's the Mare swirl in Genii and its Mare background. And just from looking at the relative locations of these things with respect to the freshest samples and to each other, it's clear that the bright swirl material doesn't represent, you know, pristine, fully immature material. Now, noticing that the smaller size range of nanophase iron has the strongest effects in the near UV, as you can see from the red and blue plots here. We infer that it's a deficit in the smallest size range that's primarily responsible for the character of the swirls. And this fits with a conclusion from David Trang and Paul Lucy, who made maps of nanophase iron abundance based on their radiative transfer modeling work. And they saw that the bright portions of swirls have lower abundances of nanophase iron. So if that's the case, then because magnetic anomalies reduce the flux of solar wind ions that reaches the surface, it would follow then that solar wind exposure is chiefly responsible for this production of the smaller size particles in normal space weathering. And then kind of as the corollary to that, micrometeoroid melting and vaporization, which takes place unimpeded in swirls as well as going on in normal non-magnetic areas, that must be the chief producer of the larger iron particles. And I think that is my last slide. I'm just going to stop there and just leave you with a gallery of Mare and Highland swirls. I didn't know Deborah was going to be taking that poll, but there's some of the contestants. So thanks.
Sorry about that, I was muted. Thank you, Dave. That was actually really interesting. We have time for one question. Tim Glotch did make a comment that I would like to echo. It's that your lack of evidence for near IR dark lane overmaturation was consistent with what Nandita just presented. And I agree with him. It's nice when you approach things from different angles and you get similar results, things that are consistent.